Hi, I must congratulate myself for not posting for 2 months. I think it's actually closer to 3, but I'm going to say 2 just to make myself feel better. My excuse is that I've lost my Apple Pencil, but also I couldn't be bothered finding for it, but I found it now. So here we are. And this is the solution, I guess, to question for you number 1. What a cringy title I chose, but you know what? Anyways, let's get started. If you haven't watched that, go watch it and you'll know what's going on. So we want to find this area, and because this is in the complex plane, let's switch this to Cartesian. And I'm just going to use Euler's formula on this. So let's pull out the 1 over root 5 and rewrite e to the I pi as cosine of pi t plus I sine of pi t times phi to the power of minus t. And we'll expand this, so we'll do real and imaginary. If I keep the 1 over root 5 out for the real and imaginary, I'll get phi to the t minus phi to the minus t times the cosine bit, and then just for safety, I'm just going to rewrite the 1 over root 5, and then I'm going to get 1 over root 5 times I sine pi t. Does it look right? No. I'm missing a phi to the minus t. There we go. And yeah, that's the real and imaginary components. And if we just switched this to x and y, that's basically what we're working with. So the imaginary component is going to be this. Great. And now that means we have a parametric equation for this curve. And to find the area of a parametric equation, you've probably seen these formulas before. And we will kind of work with both, but I also want to say where they come from first. So I mean, I'm actually not sure where, if it comes from what I'm going to show you, but I guess it just gives you more intuition. So, yeah, let's cut to another part. Okay, so to get more intuition for these two formulas, we're going to take a look at vector calculus stuff, which hurts brain, but it's fine. I also realized we missed a sign here on the last section, but you know what, it's fine. It doesn't matter because it goes around the curve. If you go around the other way, it goes negative, but it's kind of relevant to this, so it's fine. Anyways, we're going to take a look at Stokes' theorem first in R3, and then we're going to transport it into R2, which becomes Green's theorem, but I also want to talk about where that comes from. So anyways, if you don't know what Stokes' theorem is, just skip this. Or if you want to learn about it, you can learn from here, but there's probably better videos. Anyways, if you take a surface, I mean, if you know about Stokes' theorem, you probably have heard about this, intuition, but oh well. Take some surface in 3 dimensions. You've got this curve around it, and let's call the boundary C. So Stokes' theorem says that if you integrate along the curve and take the vector field dotted with the infinitesimal displacement vector, that's going to be equal to the integral over the surface of the curl of the vector field dotted with basically the normal vectors. So what that kind of means is, and the intuition for this is, the left side talks about if you add about if you add like all these tangent vectors around the boundary, well, if you add the magnitudes, I guess, of these vectors, and the right side is talking about how you add the curls, tiny curls within the surface. And what happens when you add these tiny curls? Well, this bit of the curl, well, this bit of the curl kind of cancels out with this bit of the curl because they're going in opposite directions. Same thing here. So in the end, you're kind of left with like one big massive curl. I mean, if you can't see it, if I draw a few more, this going left curl is cancelling out with this going right curl, so that cancels out as well, and then you end up with this big massive curl going around the surface, which is gonna be equal to this integral. So that's where Stokes' theorem comes from, and of course it works for any three-dimensional vector field, but we kind of want to work in 2 dimensions. And what happens when you have a surface that's completely flat, and your vector field is also completely non-existent in the z direction? Well, you can still do normal curls on it, right? Like if you consider it in 3 dimensions, just with your third component of the vector field being 0, and also your curl, I mean your curve doesn't go into the z space, I guess. If you compute the curl of it, and this is kind of normally how I do it, it's kind of abusive notation, but it works, so who cares? And the z component is 0 as always, so, well, not as always, when it's flat. So if you compute the curl, that is how you compute it, ddz and fy minus j ddx 0 ddz fx and plus k d dx fy d dy fx. And if we take a look at these determinants, that's obviously 0. How about this? Well, f of y depends on x, y, and z, right? But our z is always 0. So ddz of fy must be 0, because it's a partial derivative. So it doesn't matter. This whole thing is 0. And same thing for here as well. That's clearly 0, but ddz of fx is also 0, because the z component of fx is 0. So that's 0 as well. And we end up with k multiplied by, multiplied by dfy dx minus dfx dy. And there you go. That's kind of where Green's theorem comes from, because if you take a look at Green's theorem, this is for a 2D vector field. The left side is the same, but the right side is literally just this, right? And ds. And this is where it comes from. This now becomes a scalar. And look at this. This was a vector field dotted with a vector. And now this becomes a scalar because we're kind of encoding this k, because everything is going to be parallel to k now. So you can kind of just treat it as a scalar. And I think that's called like a pseudo-scalar or something. Don't quote me on that. But yeah, so we take this part, which is because it doesn't go into any of the other directions, and just put it straight into there. And that gives you 2D Stokes' theorem, which is Green's theorem. So we are going to make use of this just because we're working in 2D today. And yeah, so as you can see, we can now safely use a 2-dimensional vector field without worrying what the hell this means. But we just sorted that out, so that's great. And this is Green's theorem in front of your eyes again. And we're going to start. So to find the area using a double integral, usually you just do this. right? That's literally the area, because you're integrating all the tiny areas. So there's going to be a hidden 1 in there, which means if you compare this to Green's theorem, you want this bit to be equal to 1, right? And so that means you want to find a vector field such that that bit is equal to 1. And there's many choices, right? One of the choices is f equals 0, x. Why? Because del fy, del x. I don't know, I sometimes say del, but I'm just going to say d here, just because we're not doing total derivatives anyways, so... I mean, we might in a bit, I'm not sure. Anyways, it's fine, don't worry. Yeah, if you plug this in, that's literally going to be this minus d dy of 0, which is just 1. And that satisfies what we want. And I've just realized the previous section, I put the sign in the wrong integral, because that is what we're getting. Why? Because if we choose this vector field on the right side, we're going to have this this integral, 0x dot dx dy, which is just going to be x dy. There you go. Yay! And same thing, if we find, if we define f to be minus y0, then we're going to have, this is going to be 0 now, and that's going to be minus y, and that's also 1. And therefore, the right side of this integral is now, the minus y shouldn't be there, it should be up there. And that's now minus y dx. There we go. Yay. Wow. Intuition gained. Okay, let's cut to the next section now. So as you can see, we have multiple choices that satisfy this relation right here. And you may wonder, which will we use for our little area that we have? And I'm going to tell you, because I have the solution. So we're actually not going to use any of these. I mean, you could use one of these, but then if you use one of these, you have to use both, because that's just kind of how it works. But it's literally just because our parametric curve is annoying to integrate. So what we're going to use is, we're going to use this vector field right here, minus a half y, a half x. And you can see it's kind of just like the average of these two, and that's what I meant by, like, we have to use both, because we end up with something stupid to integrate. But then when you add both of them, or even though you get like twice the original amount, things cancel out, and it's nice. It's kind of like when you do like 2I equals some integral plus some other integral, but then things cancel out on this side. It's literally kind of just like that. But this, if we use this vector field, it will give us a shortcut. So let's do it. Let me just find what x and y are. There we go, found it. So x was 1 over root 5 phi to the t minus phi to the minus t cosine pi t. And y was negative 1 over root 5 phi of minus t sine of pi t. There we go. And let's just, I mean, I'm not going to plug them in. Plug them in your brain, right? And we know that when we're looking for the area, S ds, we're going to have the curve over, what was it over? It was over the vector field dot dr, right? Which is, our vector field is this, and if we dot it by dx dy, we're going to get minus half y dx plus half x dy. And of course, our curve is in terms of t, so we have to do some manipulation before we do that. But, oh, water bottle, bong. Anyways, stop moving. We're literally just gonna do minus half y dy dt and no, that doesn't make any sense. We're going to do minus half y dx dt and dt plus half x dy dt times dt, and then we can kind of factor the dt out. And so this will be our integrand, and that means we have to find dx dt and dy dt. So I'm just gonna move this down, and we'll find our integrand. Why not just pull a half out while we're at it, right? So if we pull a half out, there we go. Let's just find dx dt and dy dt. So it's going to be a bit of a pain, but I'm sure we'll be fine. So dx dt, we're going to use a bit of pulling out 1 over root 5, and let's start differentiating. So this term, wow, just moved. This term is going to be phi to the t times natural log of phi, and we're going to have to use the product tool. So let's see, let's differentiate this part first. So derivative of cosine is minus sign, which negates that minus sign, and so that's going to be sine pi t now, but we have to pull out a pi just because there's a pi inside, so pi sine pi t. And differentiating this bit, we're going to get minus, so that's plus phi of minus t. Ooh, and we're missing natural log of phi, just because of the base, and cosine pi t. I hope I did that right, and I totally did, because I totally don't have the derivative on another screen. And dy dt, this one's a bit better. It's just a product rule, so negative 1 over root 5. We're going to pull that out, and differentiating this bit is going to get us pi cosine pi t, chain rule, and negative, just because we've got this negative t up top, negative phi of minus t, and natural log of phi because of the base. Phi or phi, I'm sorry if I keep switching, but that's just a bad habit of mine. I just keep switching and I can't talk properly. Anyways, sine pi t, there we go. And why not just find this as well, right? So we got, this is annoying. So minus y dx dt plus x dy dt is going to be equal. Let's just write this out, right? So minus y is this. Well, it's this, but negative, so we're not going to have a negative sign. And we'll combine these two, 1 over root 5. So we're going to get 1 over 5 times the y bit, which is phi to the minus t sine pi t, and the dx dt bit, which is this sine pi t, pi sine pi t actually, pi sine pi t. And I also have like a massive lisp, I think. I don't know if you can hear it, but like, well, I guess it's not massive. I guess I just feel like it just because like I got braces. But anyways, x dy dt. So x doesn't have a minus sign. That does. So we're going to get a minus, combining the 1 over root 5s. And x is this. Trust me on this. I got it on another screen. But yeah, anyways, I have this like massive lisp. That's annoying. Dy dt is just going to be copying this bit down. So yeah, I got braces, and I mean, do they hurt? It doesn't hurt to talk, but like it hurts to eat sometimes. And anyways, we're done copying now. I was totally not talking just to fill in the silence. But anyways, it's time to expand this. And so we have to do it. I'm just going to pull out a fifth just outside of everything. And let's start expanding. So there, that's going to be natural log phi sine pi t. Yeah, that is going to be phi to the minus 2t pi sine squared pi t, interesting, and plus that, which is pi phi to the minus 2t, natural log phi, yes, see, I keep switching. Anyways, sine pi t, cosine pi t. This video is going to be ages if I keep talking like this. Anyways, cosine pi t, and we have a minus sign to be aware of, but I'm sure we'll be fine. So we're going to have minus pi cosine pi t. Let's do this bit, which is minus, because we've got, no, it's going to be a plus. We've got a plus and a minus and a minus. So plus times minus is plus. Yes, and natural log of phi sine pi t. And let's do this bit. And that's going to be, that is also going to be plus, yeah, phi to the minus 2t pi cosine squared pi t. And finally, this bit, and that's going to be minus, because we have three minus signs, minus phi, or phi, to the negative 2t, times natural log of phi sine pi t cosine pi t. Come on, please fit. And there we go. Yeah, no, it didn't fit. But that's it. And we can cancel stuff out. So that goes, we've got two of these. And this is an interesting bit, because, see, look, we can factor this out from both, and then we get a sine squared t plus a cosine squared t, or sine squared pi t plus a cosine squared pi t, but that doesn't make a difference, that's just one. So in the end, we're going to get 1/5 of, let's see, we're going to get 2 of this, so 2 of whatever this is, plus this bit, because we're multiplying by 1 now, and minus pi cosine pi t. And remember, this was the integrand. So, yeah, we can start integrating this stupid thing now. So we're ready to start integrating this thing. Just to remind you, we have this factor over half because we pulled that out from here. But yeah. And yeah, let's start integrating. But first, what are our bounds for t? Well, think about it. This is where it all came from, right? And the Fibonacci sequence goes like this: 0, 1, 1, 2, 3. And this is F0. This is F1. This is F2. And remember, we were looking at Ft. So it crosses 1 twice. And so our parameter t goes from 1 to 2. And so our bounds are from 1 to 2. Yeah, so let's plug stuff in. So our little integrand was 1/5. So let's actually just pull that out, become 1/10 of 2 natural log phi sine pi t plus pi times this thing minus pi cosine pi t dt. And this actually, like, this isn't bad to integrate, right? So let's just do it. If you integrate this, let's see, well, you'll get this factor out front because that's just a constant, and integrating sine will get you minus cosine, so minus cosine pi t, and you have to divide by the inner pi, so I guess this will work. And moving on, plus pi times, and integrating this, you'll have to divide by -2, so divide by the exponent, and divide by natural log of phi from the base, and then copy that down. Final one, we'll have cosine pi t. The integral is sine pi t, but we have to divide by pi. Coincidentally, we have a pi, so that's just sine pi t. Yep, and we're going from 1 to 2. So, plugging stuff in. Let's see, if we plug in, let's plug in 2 first. What happens when we plug in 2? Well, we get cosine of 2 pi, which is just 1. So we'll get 2 natural log phi over pi times 1. And plugging in 2 here, we're going to get pi over, actually, let's put this minus up there, and 2 natural log phi times phi to the -4, and minus sine 2 pi, which is just 0. So that's that, and we have to subtract plugging in 1. So plugging in 1 into here, we're going to get cosine pi. Cosine pi is -1, so we're going to get plus this, and plugging in 1 here, we're going to get positive, no, actually negative, because of the denominator. We're going to get pi over 2 natural log phi to the -2, and sine pi is 0, so that's -0. And distributing the sign, so that's going to be minus, that's going to turn to a plus, and there we go. That's it, and we have 2 of these, so let's combine things, and let's put this in front. Let's put this in front because it's positive, so 1/10, we'll put the golden ratio squared down, and write it like that, and do the same for this. So we'll put that down there, minus pi over 2 to the golden ratio to the 4th, natural log phi, golden ratio stuff, and minus 4 natural log golden ratio over pi. And we'll try to combine these 2 fractions just because the denominator is quite similar, and we'll do that by multiplying by phi squared on the top and bottom, and combining that becomes pi, that's a weird pi, phi squared minus pi divided by 2 phi to the 4th ln phi minus 4 natural log phi over pi. Sounds right. And actually, let's factor out pi here. So we'll get natural log, not natural log. We'll get golden ratio squared minus 1. But special property, golden ratio squared minus 1 is the golden ratio. So that's just the golden ratio. And that cancels out with one of these. So that's going to be cubed instead. And we're just going to have a pi at the top. And so, finally, we're going to have pi divided by 20 golden ratio cubed natural log golden ratio minus 4 natural log golden ratio over pi. There we go. And that is our area. And I would have written down my approximate area, but apparently I didn't. So, no, actually, I'm dumb. I didn't put in the 10. Oh. And so that's 2 over 5. Haha, silly. There we go. That is the final area. And yeah, as I said, I'm just gonna stick in the approximate area here. So, can you put it in now, please? There you go. Thanks. Right, see you soon.